In this week's video, we're going to be talking about cardiac muscles. First of all, the action potential that happens in cardiac muscle cells. So there are two major types of cardiac cells with different action potentials: contractile cells and pacemaker cells or autorhythmic cells. Action potentials in cardiac contractile muscle cells. These action potentials are significantly different from those in axons and skeletal muscle. The resting membrane potential is around -90, which is very close to the NERTS for potassium. Due to hypermobility of potassium, there are four major time-dependent currents involved in cardiac muscle action potentials: sodium current, calcium current, potassium current, and pacemaker currents. The phases of the action potential in contractile cells are: phase 4, resting membrane potential. The membrane potential is around -90 millivolts. The resting potential is maintained primarily by the potassium current. Phase 0, or depolarization phase, a stimulus brings the membrane to threshold. The rapid upstroke is caused by the opening of voltage-gated sodium channels and a rapid influx of sodium into the cell. These channels are similar to those in axons and skeletal muscles and have activation and inactivation gates leading to refractory periods. As membrane depolarizes, the IK1 channel mentioned in phase 4 close, stopping their current contribution. In phase 1, rapid repolarization. At the peak of depolarization, the inactivation gates on the sodium channels close, stopping sodium influx. Simultaneously, a small number of transient outward potassium channels and some calcium-activated chloride channels open, causing a brief outward current and initiating rapid repolarization. In phase 2, which is the plateau phase, this phase is unique to cardiac muscle action potentials and is crucial for prolonged contraction. It results from the opening of voltage-gated calcium channels, which activate and inactivate slower than sodium channels. Calcium enters into the cell through L-type and T-type channels. Additional delayed potassium channels also open. During the plateau, the influx of calcium roughly balances the efflux of potassium, keeping the membrane potential relatively constant and preventing rapid repolarization. This prolonged action potential prevents the heart muscle from being re-stimulated until it has relaxed, preventing tendinity. Phase 3, repolarization. More potassium channels open and the potassium efflux becomes greater than the calcium influx. As the membrane becomes more negative, the calcium channels close. This leads to a rapid return of the membrane potential to the resting level. The IK1 current becomes maximally open again as RMP is reached. Cardiac contractile cells do not typically show a hyperpolarization phase like that of other excitable cells. Action potentials in cardiac autorhythmic cells. These cells are found in the SA and AV nodes, and they are specialized for generating and conducting action potentials without external nervous system stimulation. They do not have a true resting phase. Their action potential has 3 phases: phase 4, 0, and 3. Phase 4 is a pacemaker potential. After repolarization, the membrane potential slowly depolarizes again. This gradual depolarization is called the pacemaker potential and is primarily due to the opening of funny channels, either IF channels or HCN channels. These cation channels open with the membrane hyperpolarizes and allow a slow influx of sodium. Autorhythmic cells also lack IK1 channels, which contributes to their less negative resting potential compared to contractile cells. As depolarization progresses, T-type calcium channels open, contributing to reaching the threshold. Phase 0, depolarization phase. Reaching the threshold potential triggers the activation of voltage-gated calcium channels. The subsequent influx of calcium into the cell causes the depolarization phase of the action potential. Calcium channels close more slowly than sodium channels, resulting in a wider action potential peak compared to a nerve or skeletal cells. In phase 3, repolarization, voltage-gated potassium channels open and the efflux of potassium causes the membrane to repolarize. Once the membrane potential drops below the threshold, these potassium channels close, funny channels begin to reopen, and the process repeats. When we talk about an electrocardiograph or an ECG, this measures the electrical activity of the heart by detecting currents flowing through the extracellular fluids resulting from the propagation of action potentials. It does not measure individual action potentials, but rather the summed electrical activity of many cardiac cells. So in our ECG waves, They show several deflections. During one complete cycle of the heart, we have P waves. This wave is generally during the depolarization of the atria. Depolarization starts in the SA node and spreads through the atria, causing them to contract and push blood into the ventricles. The electrical vector points generally towards the apex, and if a positive electrode is placed inferiorly, it results in upward deflection. The QRS complex, so this complex is generated during the depolarization of the ventricles. The electrical signal travels from the AV node down to the bundle of HIS bundle branches and Purkinje fibers, causing rapid ventricular depolarization and a contraction. So the Q wave is a small initial downward deflection caused by the depolarization spreading down the interventricular septum. This spread may be slightly upward and leftward initially. The R wave, which is the large upward deflection representing the primary depolarization of the ventricle muscle mass. This factor typically points strongly towards the apex. There's the S wave, which is a final downward deflection caused by the depolarization of the last part of the ventricles, typically the superior left ventricle. The vector points slightly upward for a moment. We have the T wave. This is generally during the repolarization of the ventricles. After ventricular depolarization, the cells repolarize, returning to the resting state. The repolarization process typically starts at the apex and the epicardium and moves toward the base and endocardium. The electrical vector of the repolarization points away from the positively repolarizing tissue towards the negative electrode, resulting in an upward deflection when recorded with the positive electrode placed inferiorly. The atrial repolarization wave is usually not seen on the ECG because it occurs at the same time as ventricular depolarization and is masked by the larger electrical signal from the ventricles. When we talk about abnormal ECGs, we have current of injuries. We're going to have anSTEMI and STEMI, which is when there's damage to heart cells, often due to hypoxia or lack of oxygen. It can cause them to struggle maintaining their resting membrane potential, leading to abnormal depolarizations. This creates an abnormal dipole when the heart should be at electrical rest, causing a persistent current of injury and shifting the ECG baseline. The ECG machine auto-adjusts to the baseline to filter this out, but the shift becomes apparent when the entire ventricular mass depolarizes because the dipole temporarily will disappear. When we talk about an NSTEMI, or a non-ST elevated myocardial infarction, this pattern, characterized by an ST depression, can be caused by hypoxia in the endocardium. In hypoxic endocardial cells, the ATP production decreases, affecting the sodium-potassium ATPase pump and activating ATP-sensitive potassium channels. This leads to a relative depolarization and a quicker repolarization of the endocardium compared to the epicardium. The switch repolarization vector creates a positive vector pointing towards the positive sensor. Because the normal resting baseline was adjusted upward, the current of injury from the endocardium. When the current temporarily disappears during full ventricular depolarization, the tracing drops back to the original baseline. As repolarization finishes the rest of the ventricle, the current of injury returns, shifting the baseline upward again, creating an ST depression. When we talk about a STEMI, or ST elevated myocardial infarction, this pattern is characterized by ST elevation, often indicates a transmural infarct where the damage spans the entire thickness of the ventricular wall. The current of injury from this damaged area creates an abnormal dipole and shift that rests the resting baseline downward. During full ventricular depolarization, the dipole disappears and the tracing momentarily returns to the original baseline, which appears as an upward shift relative to the depression baseline. As the non-damaged areas of the ventricle repolarize, the damaged area remains negative on the outside and the current of injury returns, causing the baseline to gradually deflect downward again, resulting in an ST elevation. When we talk about mechanisms for inotropic, lusitropic, and chronotropic actions, the autonomic nervous system, sympathetic and parasympathetic divisions help with the heart rate, contractility. We're going to start with norepinephrine and epinephrine and how it works with each of these mechanisms. When we start with those ones we're going to talk about chronotropy, which is increasing heart rate. In autorhythmic cells, norepinephrine and epinephrine are going to bind to beta 1 receptors, increasing the heart rate by increasing the slope of the pacemaker potential and lowering the threshold for voltage-gated calcium channels. This is achieved via a cascade involving adenylyl cyclase, CAMP, and protein kinase A, or PKA, which increases sodium influx through the HCN channels and calcium influx. We talk about inotropy. This is increased contractility. In contractile cells, sympathetic stimulation increases the strength of contraction. This is due to higher concentrations of beta 1 receptors in the myocardium. Activation of beta 1 receptors increases intracellular calcium. The mechanisms involve PKA phosphorylating L-type calcium channels, and ryanodine receptors and circopump activity, leading to more calcium stored and released. And we talk about lusitropy, which is increased speed of relaxation. Sympathetic stimulation also increases the speed of relaxation. PKA phosphorylation of troponin 1 and increased circopump activity contribute to faster calcium removal from the cytosol, allowing for quicker relaxation. We talk about acetylcholine, or the parasympathetic system. They're each innervated through the vagus nerve and the autorhythmic cells, and with the neurotransmitter acetylcholine. We talk about chronotropy. Acetylcholine slows the heart rate by binding to protein whose beta-gamma subunit diffuses to and opens G protein activated inward rectifying potassium channels. The resulting outward potassium current hyperpolarizes the cell and moves the membrane potential further from the threshold. Acetylcholine also decreases CAMP levels via the alpha subunit, which flattens the slope of the pacemaker channels. Both actions increase the time required to reach the threshold, slowing the heart rate. As at rest, constant parasympathetic activity maintains the heart rate below the intrinsic rate of the SA node. We talk about inotropy and lusitropy. Acetylcholine or parasympathetic stimulation doesn't do much for that. When we talk about the role of calcium in cardiac muscle contraction, we know that cardiac muscle contraction, like skeletal muscle, is initiated by calcium, but with cardiac muscle, unlike skeletal muscle, it uses different stores for that calcium. So when we talk about calcium releasing to the cytosol, the action potential spreading across the sarcolemma and down the T-tubules plays a critical role in the T-tubule membrane. Voltage-gated calcium channels open in response to the action potential. Although called calcium channels in skeletal muscle, these are mainly voltage sensors linked to SR channels. In cardiac muscle, however, calcium flows through these open L-type channels from the extracellular fluid into the cell. This influx of extracellular calcium is essential for contraction. This entering calcium then binds to calcium release channels located in the membrane of the SR. The binding extracellular calcium to the RYR channels triggers them to open, causing the release of a much larger amount of calcium from the SR into the cytoplasm. This process is known as calcium-induced calcium release. The release of calcium then binds to troponin C, initiating the sliding filament mechanism of muscle contraction. When we talk about calcium's return to the SR and the other extracellular fluids, this is so that relaxation can occur. Calcium must be removed from the cytosol. A calcium ATPase pump that we know as CIRCA in the SR membrane actively pumps calcium back into the SR for storage. Since some calcium entered the cell from extracellular fluid during action potential, it must also be removed from the cell. A sodium-calcium exchanger located in the plasma membrane moves calcium from the cytoplasm back to the extracellular fluid in exchange for sodium. The sodium gradient needed for this exchanger is maintained by the sodium-potassium ATPase pump. The strength of cardiac contraction is dependent on the amount of calcium that enters the cell. When we talk about the events that happen, we're going to talk about what happens in the left ventricle and aorta during a cardiac cycle. The cardiac cycle is a series of coordinated events involving pressure and volume changes, valve opening and closing, heart sounds, everything that's super essential for pumping blood. So we're going to start with the diastole rapid inflow. This phase begins when the mitral valve opens, the aortic valve is closed. The opening of the mitral valve occurs because the pressure in the left ventricle drops below the pressure of the left atrium. Blood passively flows from the left atrium into the left ventricle, rapidly filling it to to about 70-80% capacity. Ventricular volume increases rapidly while ventricular pressure remains low. And we have diastole diastasis, which is blood still flowing into the ventricle, but it's just slower because it's mostly already full. We talk about systole, arterial systole. The P wave in the ECG indicates a arterial depolarization. The atria contract, pushing the remaining 20 to 30% of blood into the ventricles. This occurs just before ventricular systole begins. Systole, or isovolumic contraction. Ventricular systole begins and ventricular pressure rises rapidly. When the ventricular pressure exceeds the arterial pressure, the mitral valve closes, which is going to cause the first heart sound, known as like lub. At this point, both the mitral and aortic valves are closed, and the ventricle is contracting, but blood volume does not change because there's nowhere for it to go. Then we get to systole ejection. When the pressure in the left ventricle exceeds the pressure in the aorta, the aortic semilunar valve will open. Blood is rapidly ejected from the ventricle into the aorta. Ventricular pressure continues to rise, reaching a maximum point, and aortic pressure also rises during ejection. Ventricular volume decreases significantly in this phase. When we talk about diastole isovolumic relaxation, at the end of the ejection, ventricular pressure begins to drop rapidly. When ventricular pressure drops below aortic pressure, the aortic semilunar valve closes, and this is where we're going to get our second heart sound, or the dub sound, as the aortic valve closes. As the elastic aorta recoils, causing a small sudden increase in aortic pressure, which is known as the dicrotic notch. With both the aortic and mitral valves closed, the ventricle relaxes without a change in volume. Ventricular pressure drops rapidly during this brief period. The T wave on the ECG represents ventricular repolarization. The last one is a diastole rapid inflow. Again, this is where the cycle restarts and we just go back to the beginning, and all of the steps will happen over again. The volume of blood in the ventricle at the end of the diastole is the end diastolic volume. The volume remaining in the ventricle at the end of the systole is the end systolic volume. The difference between the two is what we call stroke volume. And the injection fraction is when you take the stroke volume divided by the EDV, which is then expressed as a percentage. And that's all we have for this week's video.